So when you're going through and looking at graphs, and you're looking at the degrees of the vertices, you'll notice when you're calculating the degrees of the vertices, if you ever have odd vertices, if you ever have any odd vertices, sometimes you won't have any odd degree vertices, but if you ever do have odd degree vertices, there's always an even number. You'll notice that every time. You'll always have an even number of odd degree vertices. So you'll have 0 odd degree vertices, maybe, or you'll have 2 odd degree vertices, or you'll have 4 odd degree vertices, or 6 odd degree vertices, but you'll never have an odd number of odd degree vertices. You'll never have just 1 odd degree vertex. You'll never have 3 odd degree vertices, or never have 5 odd degree vertices. It never happens. It's actually impossible when you're dealing with an undirected graph. So here's an important theorem. An undirected graph has an even number, always an even number of odd degree vertices. Let's actually show that. Let's show that. It's not hard to show. So let's say you have V1 is your set of even degree vertices. So let V1 be the set of even degree vertices. And let V2, let's call that all the odd degree vertices. V2 be the set. V doesn't look too good, does it? Be the set of odd degree vertices. By the handshaking theorem, what the sum of all the vertices over the entire vertex set V, I'm going to call that capital V, that's the entire vertex set. The degree of, when you add up the degrees, it's going to be twice the number of edges, right? Twice the number of edges. Now I'm going to break this sum here on the left side into 2 sums. So I'm going to call this red sum right here the sum of the degree of all the vertices that range over the vertex set capital V. I'm going to break that up into 2. So first we're going to have green. I'm going to call these VJs. They'll be in V1, right? V1 was the set of even degree vertices. So we're going to have the sum of these guys, sum of these degrees. So these are all going to be even degrees. Plus the sum of, that's the wrong color, let's use a yellow. I was trying to use a yellow. Sum of the, I'll call these VKs, which are going to be in V2. V2 is the odd degree vertex set. So I'm going to call these degree of the VKs. And that's twice the number of edges. Now what do we know about these VJs? These dudes are even, right? The degrees are all even. So we're going to have the sum of these guys that have even degree vertices. Let's call it 2 n sub j, right? Evens take on the form 2 times a number. So each Vj is going to have 2 times some number, I'm going to call it nj. Alright, and then we got plus the sum of all these odd degree vertices. These are called VKs, I'm calling them. They're ranging over V2. V2 is your odd degree vertex set. This is what? Twice the number of edges. So basically what I can do here, I can subtract the green from both sides. Subtract the green. So I have the yellow, the degree of these VKs, or these VKs here, are coming from the odd vertex set, V2. That's going to be equal to 2 times the number of edges minus the green. And I'm going to factor out this, this black 2 here. I'm going to factor that out of the summation. It's going to give me 2 times the sum of the NJs. 2 of the NJs, where the NJs are corresponding to the VJs and the even vertex. All right, so notice that we have a 2 in common here. 2 in common. So what we're going to do, we're going to factor out a 2. So we're going to have 2 times the number of edges minus the sum of these NJs, where these NJs correspond to the VJs that are in the even vertex set. Scroll a little bit. Let me write that V properly, that capital V, okay. So on the left-hand side, we have what, the sum here of these VKs that are in the odd degree vertex set. But wait a second, the right-hand side is an even number. Right, 2 times a number, 2 times some integer is always going to be even. So note that the sum of the odd degree vertices, so on the left side, right, the yellow, that's the sum of the odd degree vertices. On the right, we have an even number, 2 times some positive integer. Note that the sum of the odd degree vertices is even. So if the sum of the odd degree vertices is even, that means there must be an even number of odd degree vertices. This can only happen, this may only happen if there is an even number of odd degree vertices. Number of odd degree vertices. You think about that for a second. Why must there be an even number of odd degree vertices? If you had an odd number of odd degree vertices, it would add up to an odd number, but it can't add up to an odd number, right? It has to add up to an even number because we on the right hand side of that equation we have 2 times something which is even. So there's the proof. So if someone ever tells you that there's a graph with 15 vertices, all of degree 3, that's impossible. There cannot be an odd number of vertices of odd degree. It's impossible. Okay, just so you know that. Pretty important. All right, so we want to introduce some special graphs. Now here's some terminology. Definition. The first thing we want to define is a complete graph on n vertices. A complete graph on n vertices. N is a positive integer, greater than or equal to 1. Denoted k sub n. So anytime you see k sub n, this refers to a complete graph with n vertices. It's a simple graph, so it has no loops, it has no multi-edges. It is a simple graph. With exactly one edge between each pair of vertices. Each pair of vertices. Okay, so let's say I'm talking about K1. K1. So K1 is going to be a complete graph on what? One vertex. So let's put a point. So according to how this is defined, I have to connect this point to every other point with one edge. This point to every other point with one edge. It has to be a simple graph, so we can't do loops. So there's nothing else to connect to, right? So there's nothing else to connect to, so that's it. It's just a graph with one vertex and no edges. All right, so let's say we talk about K2. K2, a complete graph on two vertices. Well, you have to first plot two vertices, and then you have to put one edge between every pair of vertices. So I'm going to put an edge between those two. And that's it. How about K3? 1, 2, 3 vertices. So the first two vertices here on the bottom, I have to put an edge between those. These two vertices, I have to put an edge between those, and these two vertices, I have to put an edge between those. So I have to put an edge between every pair of vertices. It's a triangle. Let's keep going. Let's do K4. Say K4, I'm going to spread out my vertices, kind of like in a square. So the bottom two I'm going to connect, right? There has to be an edge between every pair. The ones on the right I'm going to connect. The ones on the top I'm going to connect. The ones on the left I'm going to connect. The ones on the ascending diagonal I'm going to connect. The ones on the descending diagonal I'm going to connect. I've got to get an edge between every pair of vertices. That's K4. Now, how about K5? I'm going to have five vertices. I'm going to put them in kind of like a pentagon type shape. You don't have to put them in that shape, but it's a nice shape to put them in. The ones along the bottom I'm going to connect. The ones on the right I'm going to connect. The ones on the top right I'm going to connect. The ones on the top left I'm going to connect. The ones on the left I'm going to connect. I'm going to connect the two here. I'm going to connect the top to the bottom left, the top to the bottom right. I have to connect every pair. I'm going to connect the left to the bottom right, the right to the bottom left, and I think I've connected every pair. So it looks like we've got a pentagon with a pentagram inside. All right, what about K6? I'm going to do these in the shape of like a hexagon. 1, 2, 3, 4, 5, 6. It's a nice organized way to do it. You don't have to do it this way, but I'm going to do it. So I'm going to make edges between every pair of vertices. Edges between every pair of vertices. Every pair of vertices. So we missed an yes. We missed one here. I think that is everything. Let me see. Here, here, here. Let me just do this in red to make sure I'm going to go this one, this one, this one, this one. I'm going to go to the one on the top. This one, this one, this one, this one, this one. Then I'm going to go to the one. So we've done this one, right? Done this one, and we're going to take this one here, make sure we connect all this one, and this one we're going to make sure we got. This one already, this one already. Ah, we missed one here along the bottom. Good. This one. Then the one here at the bottom. That. Yeah. No, and we forgot. Yeah. Now, if you actually count the number of edges, here you got what? 0 edges. Here you have 1 edge. K2 has 1 edge. K3 has 3 edges. K4. Still you can count, right? It's easy. 1, 2, 3, 4, 5, 6 edges. K5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 edges. K3, that's one tough one to count. I'm sorry, K6. K6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15. I think we got them all. 15 edges. So notice what we had, what? 0, and then we added 1 to get 1. Then we added 2 to get 3. Then we added 3 to get 6. And then from 6 to 10 we added 4. And then 10 to 15 we added 5, right? So we had 1, 2, 3, 4, 5. We're going up. So anyone have a formula? A formula for how many edges Kn will have? If you play around with it long enough, you'll come up with a formula. I'll just give you the formula. Here's an important fact. There are several ways you can get this formula. I'll show you one way. Kn has n times n minus 1 over 2 edges. Let's just see if that works. So it works for K1, right? K1 has 0 edges. We plug in 1, you get 1 times 1 minus 1 over 2, that's 0. There's a way it worked for K6. K6, 15 edges, let's say. You have 6 times 6 minus 1, that's what, 6 times 5, 30, divided by 2, 30 over 2, 15, yeah, it works. Let me show you how you can get this. Several ways to do it. I'll show you my way. I'll prove this one. This one might be worth proving. It's a little tricky to figure this one out. So imagine here you have a vertex, right? Let's call it VI. So VI has to connect to all the other vertices, right? It has to connect to V1, V2, V3, V4, and so on and so forth, dot, 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 all the way to Vn. So every vertex, VI, has to connect to every other vertex through VI. So each vertex, V sub I, connects to the remaining vertices, V1, V2, it connects to VI minus 1, but it doesn't connect to itself, so you got to leave itself out. It connects to VI plus 1, and so on and so forth. It connects to Vn. Thus, what's the degree of VI? It's going to be n minus 1, right? It connects to all the vertices except itself, so you have to throw itself away. So there are n vertices in total, but it doesn't connect to itself, so it connects to n minus 1 vertices. Okay, so the degree of each vertex VI is n minus 1, because it's connecting to the remaining n minus 1 vertices. All right, now, let's do handshake didum, handshake didum. Bye handshake didum, bye handshake didum. The sum of the degree of all the vertices. Now, how many vertices are there? We're calling them n, right? So it's going to be the sum from 1 to n, degree of the VI's. It's going to be twice the number of edges, right? Twice the number of edges. And what we're going to do, we're going to replace the VI here, degree of the VI, with n minus 1. So we're going to have the sum, oh, that was supposed to be blue. The sum from 1 to n minus 1, right? N minus 1. So we're replacing degree of VI with n minus 1. That's equal to twice the number of edges. Now what happens if I add up n minus 1? N times, right? N minus 1 plus n minus 1 plus n minus 1, a bunch of times, n times. Well, you're going to end up with n times n minus 1. That's equal to twice the number of edges. And you just divide both sides by 2 and you get n times n minus 1 over 2. That's equal to the number of edges. There's the proof. Pretty nice proof, right? So keep that in mind. So if I ask you for K12, for example, how many edges does K12 have? Example. How many edges does K12 have? You could answer really quickly, right? The number of edges is what? 12 times 12 minus 1 over 2, right? N times n minus 1 over 2. It's going to be 12 times 11 over 2. So the number of edges is, what's 12 times 11? 12 times 11, I believe, is 132. Divided by 2, that's going to be, what's that? 66. So the number of edges here is 66 edges. Okay. What else do we do? So we talked about the complete graph Kn. We might just stop there and then pick up in another video.